I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the earth.
Okay, off-flight control is gonna go for landing. Edo,
go.
Guidance,
go.
Prop down,
go.
Pump,
Go.
Control,
Go.
Belt down,
Go.
We're go. Manual control, proceed.
We're go for landing. Roger, copy. Capcom, we're gonna go for landing. Good radar data. Altitude now 33,500 feet. 3 feet. 2.5 down. Picking up some dust. Big shadow. Big shadow. Contact right. Okay, engine stop.
Houston, Tranquility Base here. The Eagle has landed. That's one small step for man, one giant leap for mankind.
That was an unforgettable moment. Not just for me, Neil Armstrong, but for all of us. It was the culmination of a long and difficult effort that took the dedication of hundreds of thousands of people and cost billions of dollars. But it paid us back handsomely in new knowledge about our universe, in new technology, in national pride and security. But I'm not here to tell you about that quest. I'm going to tell you about another, which may be even more difficult to achieve, but which may pay us even greater rewards if we succeed. The quest for inexhaustible supplies of cheaper, cleaner, safer energy. Fusion energy. Just imagine what that might mean. Unlimited energy, without having to stand in line for it, without having to dig up the land, pollute the air, or risk polluting the sea for it, and without ever having to negotiate with other countries for it. If the quest for fusion energy succeeds, it would be a dream come true. There are some important similarities between fusion energy and space exploration. Like the space program, fusion is a long-term project, which demands an extremely high level of scientific and technical accomplishment. Also, like the space program, fusion probably won't be achieved without a great national commitment, a belief that we can do what is seemingly impossible. But unlike the space program, which is dedicated to getting man into space, fusion is dedicated to bringing a bit of space to man. The goal is to harness on Earth the same energies that drive the sun, where enormous gravitational forces squeeze hydrogen atoms together at temperatures as high as 15 million degrees. At these temperatures, hydrogen assumes a form not normally found on Earth. It becomes a plasma, a force state of matter that behaves very differently from the more familiar solids, liquids, and gases. Within the hot plasma, particles crash into one another at extremely high speeds. They fuse, liberating energy which boils up to the surface of the sun and out into space, eventually bathing us in heat and light. To achieve fusion on Earth, scientists at Lawrence Livermore National Laboratory in California are attempting no less than to recreate the extreme conditions that exist naturally in the core of the sun. They begin by building a giant magnetic bottle, which is the centerpiece of one of the most advanced approaches to fusion, called magnetic confinement. The most successful effort here so far is the tandem mirror experiment. It has huge, powerful magnets at both ends, which keep the plasma from leaking out and reflect it back and forth in the middle of the bottle. Now, the next generation is under construction. The Mirror Fusion Test Facility, or MFTF, soon will begin to test the magnetic mirror concept on an even larger scale. The basic objective of this approach is to heat atoms of heavy hydrogen, fusion's fuel, to sufficient temperatures and confine them magnetically for sufficient time to create a self-sustaining and energy-producing fusion reaction. Finding hydrogen atoms is no problem, They can be easily recovered from water, which means that we have enough inexpensive and readily available fusion fuel to last for many thousands of years. But heating and confining the fuel is not easy. In order to produce a usable fusion reaction, the hydrogen fuel must be heated to about 100 million degrees. That's hard enough, but confining it is even more difficult. Physicist Ken Fowler is in charge of Lawrence Livermore's mirror fusion experiments. How can we hope to hold something, fire that's 100 million degrees? Isn't that beyond the ability of any materials we have to hold?
Well, the most important thing is that we've done it. In this laboratory, we've created already temperatures of 240 million degrees. We do it using specially shaped magnets which produce magnetic fields that do the job for us.
So you hold the fire with a magnet rather than with a metallic furnace.
That's right, and in fact, this is a fire in a different sense than ordinary experience in more ways than just the temperature. If you open the door of a fusion fire, you would not be hit in the face with a blast of heat. The temperature is so high it doesn't radiate in the usual sense of the word. Lots of different things about it. Among them is that the fire is so easy to go out that we have to protect it in every way. First, we must only create this fire inside an evacuated vessel. And then secondly, we must use the magnetic fields to keep the burning gas away from the walls of that vessel. For what would happen is not that the vessel would be melted, but that the fire would go out.
So basically the fusion process is intended to be a heat source.
More precisely an energy source. This energy can be converted to heat, and that's the most obvious and likely thing to happen. Heat can make steam, steam can make electricity, for example.
When might we expect a commercial fusion energy plant?
I think it's interesting that in 1956, before most people knew fusion existed, an Indian scientist named Dr. Baba at an international conference at Geneva said that he thought that we would know scientifically whether fusion made sense in 20 years. That would be 1976. And really, I don't think he missed it very far. By the early 1970s, most of us who were then active in research said that by the year 2000, we should know that fusion was commercially viable. I don't think we missed it very far. And if we can continue the vigor in the program as it is now, the funding in the program as it must be, I think we can still make that target.
Scientists and technicians eventually will control MFTF through these sophisticated computers. They will graphically display what is happening in the system at the mere touch of a finger. Technologies such as this could hardly have been imagined when the concept of fusion originated here at Princeton University in 1951. Its basic principles were first developed by astrophysicist Lyman Spitzer.
In the late winter, early spring, 1951, my wife and I were about to leave for Aspen for a week of skiing holiday.
Great.
And my father and mother had been visiting us, and they were back in New York. And my father phoned up and said, "Well, Lyman, I understand the Argentines have beaten you. They've just announced that they've produced a controlled fusion reaction here on the Earth." It's a scientist named Richter who announced that his group had succeeded in releasing the fusion energy in a controlled manner for peaceful purposes, generation of electricity in the long run. And this was very startling, and most of the scientists that the New York Times phoned up to get their comments were somewhat incredulous, as indeed was I. But I began to wonder, if they were going to do it, how would they go about it? Mm-hmm. And so on the way out to Aspen, and more particularly during spare time out at Aspen, especially going up on the long single chairlift, no one to talk to.
Yeah.
I worked out some of the physical principles of how one might be able to achieve something of this sort, how one would hold in a hot gas so it could react and still stay hot.
At what point did you recognize that there might be an applied value, a practical application at some point to this process?
Well, that was the hope at the very beginning.
From the very beginning.
The whole purpose of this was to release an infinite energy source for mankind. It's, you know, that's been the purpose. Well, it's not quite infinite. It would only last a few billion years, but...
And the United States unveiled its most promising experimental devices.
Dr. Spitzer's original idea was to use magnets to confine the plasma in a figure-8-shaped tube called a stellarator. It was displayed to the world for the first time at Geneva in 1958 at the Atoms for Peace Conference. The conference symbolized the international scientific cooperation that has been a hallmark of the quest for fusion energy. But then, as now, the major problem to be solved was the containment of the plasma.
Unfortunately, when you hold a plasma in with a magnetic field, it tends to develop the shimmies and go into sort of a dance and gets turbulent and irregular and dashes against the wall. And that's it's these irregularities in the plasma when you hold it in with a magnetic field that provide the whole core of the scientific problem that they've been investigating since 1951.
The first real breakthrough in confinement was achieved by the Russians, who developed a donut-shaped device called a tokamak in 1969. Less complicated than the stellarator, the tokamak configuration enabled it to generate a stronger magnetic field using less energy. The tokamak concept has been carried forth dramatically by American scientists and engineers who are now building one of the world's largest and most advanced versions. Inside this massive structure is Princeton's Tokamak Fusion Test Reactor, or TFTR. It represents the first stages of a bridge between the experimental plasma generators and a fusion reactor capable of generating electricity.
Substructure to the tokamak, this center section through here is 6 foot thick. It is stainless steel, non-magnetic, and we keep the dielectric shield.
When completed, the TFTR will hopefully be the first to do what no other fusion device has ever done: achieve break-even, the point at which as much energy is produced by a fusion reaction as it takes to create one. Break-even is high drama expressed in the dialogue of science. A spike on a graph, a set of numbers on a computer printout. Its meaning is exhilarating to the scientists, for it marks the transition to the tangible, the moment when theory may become practice.
In fact, it's a test to see that we've got a full square.
When you actually see the scale and complexity of the construction going on here, and you realize that it's going to cost about $300 million to build this facility, that after 30 years of research will only just possibly be capable of producing a little more energy than it consumes, you can't help wondering. But I'll tell you, we didn't reach the moon with the first rocket either.
From the early experiments of American pioneer Robert Goddard, who fired the first liquid-fueled rocket in 1926, to the Russian Sputnik, the cosmonauts, the American space program, progress was measured in increments so small they sometimes seemed infinitesimal. Occasionally, progress was even measured in minus signs. I remember my own close call with this lunar landing trainer. And the challenge of developing boosters powerful enough to lift us free of the Earth's gravity, much less carry us to the moon, frequently seemed insurmountable.
And so it has been with fusion energy. Some blind alleys, a few false starts, but finally on the right track, and perhaps just in time.
The world today runs on energy that has been stored over a period of 6 million centuries as fossil fuels. In the last single century, we have used them to create the richest and most advanced civilization in the history of man. Unfortunately, we have also used our fossil fuels at such a rapid rate that we may soon run out of them. The problem has been graphically plotted by geologist M. King Hubbard. For more than 5,000 years, earlier civilizations rose and fell without touching nature's storehouse of fossil fuels. But suddenly, in a fleeting second of geological time, we are in the process of consuming them all. Unless we want to return to a considerably more primitive form of existence, we must begin to augment our dwindling supply of fossil fuels with alternate energy sources. fusion can play an important role, as physicist John Emmett explains.
Right now. You know, if I were to draw an analogy for the moment to the space program, there was a lot of technology development of rocket engines and so forth, and all of a sudden there was a point at which people decided, let's go to the moon. And a major national commitment of human and intellectual and financial resources was brought to that, and we decided to do it, and we decided to do it in a decade. That kind of thing can be done in the fusion world too. Once we have proved the scientific principles, once we have made the laboratory demonstrations, we can make those demonstrations in this decade. And then after that, we can see the first operating reactor.
If it's going to take this decades, is it really necessary that we make this commitment now, is it spend these resources now, do this development now?
Well, Neil, I think that's a very honest question. I think that the way you have to look at this sort of thing is the United States is a rich enough country, and we have enough energy reserves that your generation and my generation can get through their lives all right. But the fossil fuels we're using today are running out. They're going to be running out on our children. They're going to be running out on our grandchildren. They're running out on our allies and friends around the world right now. You know, one of the things that has made this country just fundamentally great is the willingness of its people to sacrifice now so that their children, their grandchildren, can have a better world and a better life. We've always tried in this country to make the world better for the people that follow us, rather than just live for ourselves. And fusion is a long-term commitment. Every day we put it off today, it will put it off for our children. And we have the economic strength to do it today. We have the technological strength. And if we have the will to do it today, we can get it done. I can't guarantee that when the energy prices are extremely high and the economy is suffering, that we'll have the strength to get the job done. And so I think we ought to do it today. It's a commitment that we ought to make to those who follow us.
I guess our every goal is to leave the world a little better than we found it.
We should try.
But even if fusion energy does prove to be both economical and inexhaustible, there remains a nagging question still to be answered. The sad fact is that virtually all of our present methods of producing energy are neither completely safe nor completely clean. Can we expect fusion to be any less polluting, less dangerous? Dr. Melvin Gottlieb, professor of astrophysical sciences at Princeton's Plasma Physics Laboratory.
I think it will be very safe in the sense that, for example, it cannot even conceivably explode. It cannot conceivably melt down. That sort of accident is not possible. On the other hand, there will be pollution associated with it, which we feel will be quite moderate compared with others. Therefore, one always has to make these comparisons. We feel that fusion may well represent the best compromise in terms of insults to the environment and insult to the pocketbook. And of course, it does represent, in principle, in the various forms of fusion, an infinite source of energy.
Indeed. Fuel's available every place.
The fuel is there and in huge quantities.
Indeed. Do you see the next generation or two as being characterized by continued international cooperation in fusion research, or might it turn into competition? What are some of those aspects?
Well, it has always been my belief that international cooperation would work very well until there was a product line.
I see.
We're not ready yet to produce a product line, and therefore cooperation continues to work. At some time in the future, I would fully expect and indeed hope that we will be in a product line, that there will be many technical tricks, and the various nations will say, that's enough now. We're going to develop our own line. There are major programs, of course, in Western Europe. There's a major program in the Soviet Union, a major one in Japan, and many others as well. We believe, and I think our colleagues abroad would agree, that we're now in the lead. And while we enjoy cooperation very much, we also enjoy being in the lead. And we would hope that as a result of this lead, that we can be ahead in the technology as well. After all, in the future, if fusion is a practical source of energy, there'll be hundreds of billions of dollars, in fact, thousands of billions of dollars invested in fusion energy plants. Someone's going to produce them someplace. I hope we are the ones who do so.
Not all of America's fusion research is being conducted at national laboratories or funded by the government. Nor does all fusion research revolve around magnetic confinement. Here at the University of Rochester's Laboratory for Laser Energetics, American industry has taken a serious interest in a promising alternative approach to fusion called inertial confinement.
The project is called OMEGA, and it uses laser beams to create the high temperatures needed for fusion. The fusion fuel, in this case a perfectly spherical pellet smaller than a grain of sand, is loaded into the target chamber. OMEGA's 24 laser beams are tightly focused on the fuel target. Hundreds of megawatts of electricity, equal to many times the power generated by all the plants in the United States, are transformed into a single, brilliantly intense pulse of light.
7, 6, 5, 4, 3, 2, 1, 0.
The incredible burst of energy compresses the core of the pellet to a density 1,000 times that of a drop of water. The temperature of the pellet reaches 100 million degrees. A fusion reaction occurs. Because it all happens so fast, in less than a billionth of a second, the plasmas are confined by their own inertia, and so the giant superconducting magnets needed for other fusion approaches are unnecessary.
Among the principal sponsors of this experiment is Ohio, whose vice president for research and development is Dr. Moshe Lubin. Dr. Lubin, why is private industry involved in this project?
There are a number of reasons. First, it's energy. Energy is, especially nuclear energy, is definitely an increasing mix of the energy economics as we look into the future. Secondly, it's new technology. The technology involved in inertial confinement fusion is a technology which is literally forefront across the board and has application and spin-offs to a whole variety of other energy-related technologies that we see coming down the pike in the relatively near future. Third is people. People are the most important ingredient we have to worry about in training those leaders that are going to populate this industry in the future if we're really going to become strong again in our utilization of energy resources. Last, and it's probably somewhat philosophical, is a recognition by large energy industries that we have to get in on the ground floor. The past philosophy of letting Uncle Sam do the work early on, and then when it becomes interesting commercial for industry to pick up the ball and run with it, I think is a concept that ought to be re-examined, with industry being asked to commit very early on in the program to make sure that the ultimate result is in fact timely and applicable to the economic development of our country.
Well, magnetic confinement and the inertial methods, as evidenced by OMEGA here, are making good progress. Can't we pick one at some point in time here and bet our money on it?
That sure is tempting. It's very nice to have only one particular approach that you have to work on. However, I hope we don't do it. This is a very early stage of the evolution of what turns out to be, I think, very promising families of technologies. We're talking about implementation 25, 30, 40 years down the road. And it is not terribly important to ask the question at this point in time, which is ahead. What is important is to allow those to pursue their paths of development to the point where real hard economic decisions and high probability decisions can be made.
Within the next decades, various approaches to fusion will lead to further milestones. And finally, commercial electric power. But in the meantime, there is a need to know more. It makes good sense to pursue the development of a number of promising possibilities. But no one should minimize the tremendous problems and costs still to be encountered. For fusion is truly one of the most difficult scientific and technical tasks that mankind has ever undertaken. The challenge is great, the promise is greater, the need greater still. Now is the time for the nation to take longer strides, to undertake a great new American enterprise. President Kennedy said that when he committed America to placing man on the moon. Such a time may be here again. The quest for fusion energy could very well be the next great American enterprise. The decision to pursue it is vital to us all.